Okay, recording. Now, in number 4, well, first one for 1 mark, that's nice and easy. Define density. What's density? Yeah, density. But actually, let's see what he writes. Yeah, exactly that. Mass per unit volume. So, I mean, that's a 1 mark. Okay. B. A block of brass is 30 centimeters by 5 centimeters by 4 centimeters and is 70% copper and it's 30% zinc. And the question is, get the volume, the mass of copper, the mass of zinc, and the density. Okay. So firstly, the volume. Well, that's nice and easy. You just multiply them. 0.30 times 0.05 times 0.04. So the volume equals 0.0006 meters cubed. Oh, by the way, at the meeting, did you ask for more physics classes?
Oh, yeah.
Yeah, you did? Yeah. Okay, right. You said 12 hours. Is it per week you were looking for?
No, it's 20.
20, oh yeah, okay. In fact, just cancel English and replace by physics, yeah?
Definitely, most probably.
Yeah.
I would vote for it.
I was going to say more useful, and then I forgot that this was recorded, so I won't.
But you just said you were going to say...
I won't. I'm going to say, in fact, you should have more English classes and other subjects too.
No, English is one. Nobody watching the video other than us.
Maybe it'll go viral.
Seriously.
Alex.
Even Einstein's video, because of the even if Einstein had a video.
Yeah, you're right. It's unlikely that this video will go viral unless we end it with like a Harlem Shake or something. But not likely. Okay, part 2 is calculate the mass of copper used. So this is the volume for total. So for copper, let's get how much that is. It's 70% copper. Now, is that percentages? Yeah, 70. Okay. Well, firstly, formulas. Density is mass over volume. What do we want? Mass. So that's density times volume. Now, he gives us the density of copper. It's 8.93 times 10 to the 3. But we need to know the volume. Well, the volume would be 0.0006, but it's 70%, so I multiply by 0.7. Yeah, I don't have the space for the 0. So when you put that in, you get 3.75?
Yeah.
Okay, 3.75. Now, I'd like you to do the same thing, but this is now for the, what's next? The zinc. So the only thing you need to change for the zinc is here is 0.3, and here for zinc is 7.14. So when you change them, what do you get? 1.29 kilograms. Okay, and finally, he wants the total density.
Kilograms? Grams?
Sorry, what am I doing? 1.29 kilograms. Now, finally, he wants the total density. What's the total density? It's the total mass over the total volume, which in this case is, 0.0006. So that works out as 8.4, times 10 to the 3 kilograms per meter cubed for volume. 1, 2, 3, 4, 5, 6, 7 marks. Okay. This is now used to make wire, and the wire is 0.84 millimeters in diameter. So you take all of this, Can you picture it? You take it all and you melt it, and then you roll it out into a wire. So the wire, what type of shape is a wire?
Cylinder.
It's basically a long cylinder, okay? And he wants the length, and he gives you the radius is 0.84 over 2 times 10 to the minus 3 meters, okay? So what formula should we use here? What do we know about this cylinder? We know the volume.
Yeah.
So the volume equals, we got it earlier, didn't we? Yeah, no, we know it, 0.0006. And that must equal, what's the formula? Pi r squared length. So if I just divide by pi r squared, there we go, I can get the length. So what's the length here? It works out as oh wait, cross section with a no, that's okay, sorry, yeah. I'm getting very small answer, yeah. What did you get, Brandon? Oh, actually, no, sorry, the next page. Oh, yeah, what did you get?
1083.
Yeah, 1083 meters. Okay. Right. Next one now. D. So they have a graph here. And the graph is force versus length. Ah, yes. And the first one is, what is stress? What's stress? Yes. Yeah, I always have to think for a moment too. It's force per cross-section area squared. Now the only reason I say cross-section, force per, I should actually really write the word unit in here as well. Unit cross-section squared. Cross-section just meaning the, you know, the area at the tip if you're looking down it. And what's strain? No, that's Young's modulus you're thinking of. Strain? What is it? Yeah, it's the extension over, no, it is this. Extension over natural length. Yeah, the formula is delta x over x, yeah. Sorry, because he's asking you to explain, I shouldn't write the formula down. I should write it out as strain is the extension in the length per natural length, or unit natural length. Okay? But you get the idea anyways, okay? Now, part 2, they use strange Roman numerals here, capital part 2. Use this data to calculate Young's modulus. Okay? So, let's look at it like this. What is the formula for, I'll go to the next page actually. What is the formula for Young's modulus? Stress, whoops, over strain. Now, what is the formula for stress? Very good. And for strain? Delta x over x, the natural length. Maybe I'll call it L or something. Okay. Now, if I just rearrange this a little bit, I get delta x over L times E equals F over A. I just took this up to the left, yeah? Is that okay? And then if I just do one more piece of rearrangement, if I take the A up here, I get AE over L times delta x equals F. Or if you want to even make it extra clear, F equals AE over L times delta x. Does this look familiar?
equals kx.
Yeah, it's like Hooke's law, F equals Ks. LF. Now, actually, sorry, I misread it. He doesn't want the K. I thought he wants the K. He wants the Young's modulus. So if you look at our graph has length and force. Okay? Young's modulus is stress over strain, force over area. Yeah, actually, by the way, what I just wrote here, you don't need it for this question. But I'm not going to say forget about it. He could have as easily as asked for Hooke's constant K. So you have to do this little bit of rearranging to see that the K is actually this formula here. Now, do we know the A, the area? We do. Do we know the natural length?
Yeah.
We can do, yes. And do we know the E? We don't. If I knew the E, I could then find the K. Anyways, let's go back to our graph. So let's take 2 points on our graph. I'll take the point at the beginning. What's that? It's not very clear. Can somebody give me their best guess of what they think it is? So the force is 0, and what's the length?
3.295.
6.5.
296. Yeah, 64. And then let's take the point at the end. It's 203.2988. Okay? Now, Young's modulus is stress over strain, which is force over area, all over the extension, which is delta x over x. Now can I use this point? No, why not? Because what's the delta x here? 0. Okay, so I must use this point. What's the force? It's 200. What's the area? What's the area? It was given earlier. Where is it? Oh, we have to calculate it. Yeah, we didn't actually calculate it. It's pi r squared, and the radius is, what was it, 0.84 millimeters, wasn't it? So 0.42 times 10 to the minus 3 squared. Okay. Now, what's the natural length? Well, if you look at your graph, the natural length is here when there's no force. So that is 3.2964. And what's the extension?
This is 3.296 minus 3.
Very good. It's the difference between the two. So that is 3.2964 minus 3.2988. Oh, sorry, the other way around. 0.0024. Sorry, that's a bit messy, but when you put them all into your calculator, you get 4.96 times 10 to the 11. Is that right, Brandon? Just look, it doesn't matter. Just put it into the calculator and out comes the number, okay? Right. Yeah, we've seen this one again before, the ductile material. Draw a sketch graph to show how it changes. Did I skip by something? No? Okay. So, what's the graph? Look here, what happens with the graph? At the beginning? Oh, sorry, wrong way around. At the beginning, you increase the force, and what happens to the length?
It increases.
Yeah, or if you want to use the extension, you could do that as well. I don't really see a problem with that. So at the beginning, when there's no force, is there any extension? No. And then when you increase the force, what happens? It increases steadily, like this. But then you reach a critical point where you kind of lose the stretchiness, you know, and instead of getting more force, you don't, and it kind of just flattens off. This here is called the elastic limit, isn't it? Let me check. The limit, just the, yeah. This is the limit, or the elastic limit. Now, the name of this piece here, after the limit, does anyone remember what it's called? It's called the plastic region. And then, before it snaps, or not snaps, before it loses its stretchiness, what's this part called? It's called the elastic region. Okay, so I don't have anything that's kind of stretchy like this, but what you're picturing is like a rubber band. You stretch it, and then you get more force. But if you stretch it too much, it kind of, not that it breaks, well, maybe not a rubber band.
Yeah,
Like
like,
it will go
like a
up.
cube. Brutal.
Like a solenoid or whatever that thing is called. The rings that you stretch too much, they don't get back to their position.
Yeah, if you stretch it, yeah, that's it. If you stretch it too much,
It starts to lose the force. And
yeah, it loses the force inside, it doesn't stretch back. So as long as it's still stretchy, that's called the elastic region. And then as soon as it loses its stretch, it's called the plastic region. And the cutoff point is the limit, or the elastic limit. Say again?
Like
The slinky.
yeah.
It's called the slinky, yeah. You know slinky?
yes.
That's the code.
But like the spring.
Yeah.
My
You know the one, you put it, goes down the stairs.
I know. But isn't it called something else?
In America it's called slinkies. I don't know what else it's called.
American English is not English.
What? What did you say?
American English is not English.
My wife's American.
I didn't mean that.
Continue talking about this retirement plan. If you like, I can contribute to it. If you want to start sooner.
Yeah, I'll stop right now.
Good idea. Okay. Stop that one.